Want to put together a sample exam, 5 notations here for you. Number 1, determine whether B is in the column space of A, and if so, express B as a linear combination of the column vectors of A. To show that B is in the column space of A, you simply solve the system. So here, so we solve I did it do that. And when you solve this, sorry about that. One, -3, 1. And so that all checks out good. So then it says, so if you can solve the system and you get the unique solution, then that simply means that B is in the column space of A. If that be the case, then it says express B as a linear combination of the column vectors of A. We take these numbers, 1, -3, and 1. Those are coordinates, components, if you will. So 1, this 1 times the first column plus the -3 times the second column plus that last 1 times the last column. We check that as 1 plus 3 is 3 plus 1 is 5. This is 9 minus 9 is 0 plus 1 is 1. This is 1 minus 3 is -2 plus 1 is -1. So you've expressed B here as a linear combination of each column. So it's 1 times that column 1, just write that, plus the -3 times column 2, plus the 1 times column 3. And that gives us B. Number 2, this is the superposition principle. For vectors. So it says find the vector form of the general solution of x equal to 0. We call that the complementary solution, which consists of the linear combination of the basis for the solution space. So C1 times V1 plus, and so on, plus C sub n times V sub n. Now, how does that look? Well, we have 4 variables, x sub 1, x sub 2, x sub 3, x sub 4. Now, x sub 1 is said to be 2r plus 4s. X sub 2 is r minus 5s. X sub 3 is r. X sub 4 is s. So this is, in terms of the r's, this is 2, 1, 1, 0 terms are, plus now in terms of the S's, 4, negative, 5, 0, and 1 times S. So if you think about it, the V1 would be this vector here with 2, 1, 1, 0 in it, and the C sub 1, the coefficient or the scalar would be R, and then here V sub 2 would be the 4, negative, 5, 0, 1, and then with this scalar being S or C sub 2. So then it says find the vector form for the general solution. So the general solution is said to be a particular solution plus the linear combination of the complementary solution that you got from the basis for the null space. So the particular solution is given here. So a particular solution would be x sub 1 is 1, x sub 2 is 2, x sub 3 is 3, x sub 4 is 4. Then plus now the general solution for the null space. Well, that's all you need there. Now number 3, find a basis for the null space of A. You can take that matrix A and reduce it to reduce for echelon. Notice that rows 1 and 2 are multiple, so row 2 goes out. Row 3 is just 0. Then after that we can divide everything in row 2 by 2, excuse me. That gives us 1, 0, 1 half, 0, 0, 0, 0, 0, 0. Well, you look along the main diagonal and notice that you have a leading 1 at that first position. That tells you that the basis for the row space will only be just that one row. But the basis for the null space would consist of the terms whereby x sub 2 and x sub 3 are said to be arbitrary. So here we set x sub 2 to equal to S and set x sub 3 to equal to T, just any real number. And notice that we get for x sub 1 is equal to 1 half T. Right. So you see that because it's the first row is x sub 1 minus 1 half x sub 3, which is now T, is equal to 0. So x sub 1 is indeed 1 half T. So we have here x, this x represents the basis for the so-called solution space. The solution space just happens to be the null space. X sub 1 is 1 half x sub 2, this is 1 half T, x sub 2 is S, x sub 3 is T. So we can write that by using the associative property. Start with S first, doesn't matter, and then with T. So the basis for the null space is the first vector 0, 1, 0, and 1 half, 0, and 1. The basis for the row space, we reduce the matrix. We have a leading 1 at the first row, so all we have is R sub 1 is that first row. the basis for the column space, C sub 1. That corresponds to the first column where we have the leading one. Find a basis for the row space of A consistent entirely of row vectors of A. Well, we only had one vector for the row space, which that corresponds to that first row, which has 2, 0, and -1 as entries. Find the rank of A. There's only one basis for the row space, so the rank is 1. And the nullity corresponds to the null space, the number of vectors we have in the null space. There were 2. So the nullity is 2. Numbers 8 and 9. Here we want to find the characteristic equation. Well, that which is this. My space may run out, so let me just use this part here. The characteristic equation is the determinant of lambda times the identity minus A, which that gives us lambda plus 2, 0, -1, +6, lambda plus 2, 0, -19, -5, and then lambda plus 4. We simplify that. We just solve for that determinant. I use cofactor expansion along the first row. So that's lambda plus 2 times the determinant of the submatrix found by deleting the first row and first column. So it's lambda plus 2 times lambda. I better write it all in there. Hopefully my space would be okay. And then this is plus, then you go to that -1 times the matrix of its determinant, which is delete this row and column. So we have here 6, -19, lambda plus 2, and -5. So here we get lambda plus 2 times lambda plus 4 minus 1 times -30 plus 19 times lambda plus 2. We simplify that. This is, I'm missing this is lambda plus 2. I forgot that. Times lambda plus 2 times lambda plus 4. That's lambda plus 2 to be squared. So this is going to be lambda squared. When I FOIL that out, plus 4 lambda plus 4 times lambda plus 4. This is minus -30 plus 19 lambda plus 38. So this is, distribute all this out. This is lambda to the third plus 4 lambda squared plus 4 lambda plus 4 lambda squared plus 16 lambda plus 16. This inside the parentheses is 8 plus 19 lambda. So this is +8, negative, so it becomes -8. And then this is minus 19 lambda. So we get lambda to the third, looks like plus 8 lambda squared plus 4 lambda, 16 lambda is 20 lambda, minus 19 lambda is just lambda. And so we have lambda, 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 which I'm thinking about a crazy comedy movie from the 80s. Anyway, 16 minus 8 is plus 8. That's set to equal to 0. Now that's the characteristic equation. I would need to, you can use synthetic division to break that down, or you can just factor by grouping. There's some commonality there, so Let's go ahead and just factor by grouping. You can factor out a lambda squared from the first two terms. You have left lambda plus 8, and then take out a plus 1 from the last two terms, lambda plus 8. So factor out lambda plus 8 from these two expressions. We have lambda plus 8 times lambda squared plus 1 equal to 0. That's the characteristic equation simplified. Now the eigenvalues, when you set that equal to 0, we get lambda equal to negative 8, lambda equal to plus or minus I, so we get I, and then lambda equals to negative I. We'll only consider the real value in terms of solving for the eigenvector, so we want the so-called the real eigenvector. So we let lambda equal to negative 8. This implies that we have negative 8 times the identity minus A. So we just plug in the negative 8 up here. It's a matrix now. So it's negative 8 plus 2, negative 6, 6 there, negative 19, 0. Negative 8 plus 2 is negative 6, negative 5, so 1, negative 1, 0. And then negative 8 plus 4 is negative 4. Reduce this matrix down, and when you do that on your graphing calculator, you end up with 1, 0, 0, 0, 1, 0, 1, 6, 1, 6, and 0. So here, notice that this is x sub 1 plus 1, 6, x sub 3 equal to 0. And the second equation is x sub 2 plus 1 over 6 times x sub 3 is equal to 0. So x sub 1, x sub 2 depends on x sub 3. It's a dependent system. Well, we've actually forced it to be making use of the concept of the characteristic equation or the so-called eigenvalue. The eigenvalue forces this guy to give us a determinant equal to 0. If the determinant is equal to 0, that means that the system is linearly dependent. So we take a good system, we break it, because we want to use the fruit of this to fuel some very neat and important concepts in mathematics. So we set x sub 3 to be some arbitrary term, number. And so that means that x sub 1 is equal to negative 1/6 t, and x sub 2 is equal to negative 1/6 t. So here, the eigenvector that we want is x sub 1 is negative 1/6, x sub 2 is negative 1/6, and x sub 3 is 1 times t. So the only real eigenvector is this guy, negative 1/6, negative 1/6, and 1. Now the last problem on the test, I'm going to ask you to state 15 equivalent statements of the monster theorem. There's about at least 15 there. It's a little bit more, but the ones that deals with the orthogonal space and the orthogonal complements, we haven't covered that yet. So give me 15 and then you'll get 10 points for free. Well, that'll do it. Thank you.